Now in today's class we will study about line spectrum of hydrogen atom, right? And then first we will see the arrangement to produce line spectrum of hydrogen atom, and then we will see the explanation of the line spectrum, right, on the basis of Bohr's model of atom, how Bohr's model of atom can explain the spectrum of hydrogen atom, right? So spectrum is mainly obtained, right, when suppose you have a discharge tube, right? If this is the discharge tube, right, this discharge tube contains hydrogen at low pressure, right? This contains hydrogen gas at low pressure. Why low pressure? If you remember the discharge tube experiments that we have studied earlier, there I have given you the reason, so you can look at that lecture in case you have any doubt with the discharge tube experiments, right? So when this tube has hydrogen gas, when electric discharge is passed through this discharge tube, right, then there are some radiations that are coming out of this discharge tube, right? So when this radiation is passed through a spectroscope, right? Now what is a spectroscope? Spectroscope is a device, right, that is used in spectroscopy, right, which will resolve radiation into its constituent wavelengths, right? So what I mean is the radiation that is coming out of this discharge tube, right, it consists of radiations of multiple wavelengths. Lambda indicates wavelength, right? Radiations of multiple wavelengths, right? So since it contains radiations of multiple wavelengths, so we need a way, right, to resolve these multiple wavelength, right, or to resolve this radiation, right, that is coming out of this tube into its constituent wavelengths, right, to resolve this radiation into the wavelengths or resolve it into the radiations that it consists of. So when this radiation is allowed to pass through this device, right, which we call it as spectroscope, right, this spectroscope will resolve this radiation into its constituent wavelengths, right, like this. This is your radiations of multiple wavelength, lambda 1, lambda 2, lambda 3, lambda 4. This is your spectroscope, right, or we also call it as spectrograph. Now if you have a telescope here, in this arrangement you have a telescope, right, and here some scientist sitting, right, can look at these radiations, right, he can observe these resolved radiations, right, which is resolved by this spectroscope. This is your basic arrangement of spectroscopy, or basic arrangement to obtain the line spectrum of hydrogen atom. I just quickly recap. This is the discharge tube that contains hydrogen at low pressure, right? When electric discharge, right, is passed through this discharge tube, the radiations that are coming out of this, you will see some radiations that are coming out of this discharge tube. When these radiations are allowed to fall on this spectroscope, or when these radiations are passed through this spectroscope is nothing but a prism, right? It has a resolving power. It will resolve the radiations that consist of multiple radiations or multiple wavelengths, multiple radiations of different wavelength into its constituent wavelengths, right? Suppose this radiation consists of 4 different radiations of different wavelength, so this spectroscope will resolve it into its constituent wavelengths. Now the observer here, right, can observe these resolved radiations through this telescope, right? Now, since we said a line spectrum, we want a line spectrum. So what we will do is we will replace this telescope with a photographic film, right? And when these radiations are allowed to fall on this photographic film, you will observe group of closely spaced lines on this photographic film. Right? These are group of closely spaced lines. So this group of closely spaced lines which are formed as a result of excitation of gas in this discharge tube, right, is known as your line spectrum. This is your line spectrum, right? We also call this line spectrum as spectrogram. Spectrogram, right? And this is your photographic film, which is used to observe or which is used to obtain this line spectrum, right? Now, what this line spectrum is basically, since this is a photographic film, so this line spectrum is basically a picture or a photograph of the radiations that are coming out of this discharge tube, right? I'll just write it over here. This line spectrum is basically a picture of radiations, right? Line spectrum is picture of radiations, right? These radiations that are coming out of this prism or spectroscope, when you obtain it on photographic film, you will obtain these lines, right? And these lines are nothing but every line corresponds to a radiation of specific wavelength, right? So every line in spectrum corresponds to a radiation of particular wavelength. Right? So all these lines are nothing but these radiations, right, of specific wavelengths, lambda 1, lambda 2, lambda 3, lambda 4. Right? So this is the basic arrangement to obtain the line spectrum of hydrogen atom. Now we will try to understand the reason for this line spectrum based on the Bohr's model of atom, right? How Bohr's model of atom can explain this line spectrum. Okay, one important thing is about line spectrum that, just made it like this. One important thing of line spectrum is that this line spectrum is specific to specific element, right? No two elements can have same line spectrum, right? For example, if I want to obtain the line spectrum of sodium, if I place sodium here and I heat it, right, the heated sodium will emit radiations which will get resolved through this spectroscope, right? And when the resolved radiations will fall on this photographic film, we will obtain yellow lines in case of sodium, right? Yellow lines of wavelength, I think it's 5890 to 5858 yellow lines of wavelength corresponding to 5896 and 5890 angstrom, right? And the spacing between these lines is also specific to specific elements, right? So line spectrum is specific to specific elements. So it's like, since I said that no two elements can have same line spectrum, that means if you have a line spectrum of an element, right, you can recognize which element this line spectrum belongs to, right? Like I said, in case of sodium metal, the line spectrum that you will obtain on the photographic film consists of yellow lines, right, of wavelength 5890 and 5896 angstrom, right? So line spectrum is specific to specific wavelengths. These are like fingerprints, right? Like we have fingerprints, right? No two humans, right, have their similar fingerprints. Similarly, no two elements will have similar line spectrum, right? So line spectrum is specific to specific elements. If you place sodium here, so in place of sodium, if you place potassium here, maybe the line spectrum, the color of line spectrum is different, right? The wavelength, right? Because we said that the lines are nothing but the waves, right? The radiations, right, of different wavelength. Every radiation of different wavelength will form a line on the line spectrum, right? So every element will form a different pattern of line spectrum, and the spacing between the lines, right, will also be different, right? And I just mention it over here, spacing between lines is also different, right? So this is your line spectrum. Now we will study about the line spectrum of your hydrogen, right? Emission spectrum of hydrogen based on Bohr's model. But first, if we just look into the photographic plate, how it looks like in case of hydrogen atom, in case of radiations that are coming out of this discharge tube that consists of hydrogen atom, it somewhat looks like this. It consists of lines of different wavelengths, closely spaced lines, right? This is the kind of spectrum that you get for hydrogen atom emission. This is the emission spectrum of hydrogen atom. Now let's quickly understand it, the formation of line spectrum based on Bohr's model of atom. Now there is a point in the Bohr's model of atom which says that an electron will continue to revolve, right, in its specific orbit, right? And when it is given energy, right, when that atom is excited, the electrons in the atom will absorb energy, will move to higher energy state, right? And we have studied that the higher energy state is short-lived. It's an excited state, right? And electron will stay in that higher energy state only for a short period of time, right? And it will transition back to its ground state. It will come back to its ground state of lower energy, right? So when electron will move to a higher energy state, it absorbs radiation, right? And when it will come down from higher energy state to lower energy state, it will emit radiation, right? So when it will emit radiation, right? Similarly, if you have hydrogen here, we have hydrogen here. So when you passed electric discharge, what that electric discharge did, it excited the hydrogen atoms, right? When hydrogen atoms get excited by receiving energy from electric discharge, the electrons in the hydrogen atom moved to a higher energy state, right? And when those electrons in different hydrogen atoms returned to their ground state, right, they emitted radiations. So these are those emitted radiations which are formed when electrons in the higher energy state are moving back to their ground state. So when these radiations are resolved by this prism, which is a spectroscope, right, these radiations are resolved because these are different radiations of different wavelengths. We will understand why different radiations of different wavelengths. These radiations of different wavelengths, right, when fall on this spectroscope will resolve these radiation into the constituent wavelengths, into these constituent radiations of different wavelengths. When these will fall on this photographic film, it will form this line spectrum of hydrogen atom. So these line spectrum, the lines that you see in this spectrum is nothing but these are waves, these are radiations, right, that are formed when excited electrons in hydrogen atom are returning back to their ground states, right? So when these radiations, right, that are as a result of electrons coming back to their ground state, right, will fall on this photographic film, every radiation will form these lines, and these lines are waves of different wavelengths, or these are radiations, right? These are radiations of different wavelengths that we see here in this form of spectrum. Now we'll also understand how different wavelengths, how lines of different wavelengths are getting formed, right? We'll understand this in a while. So here, let's quickly understand this based on the quantitative relations that we have seen in the Bohr's model of atom. We said that if this is the higher energy state, let's say these are, and this is the nucleus, right, that contains protons, neutrons, and these are different energy states E1, E2, E3, and we know that as we keep moving away from the nucleus, the energy of these shells will keep on increasing, right? And one very important property of this electron is, when this electron, the energy of this electron, when it is moving in that energy shell of fixed energy, right, that orbit of fixed energy, because as per Bohr's model, the electrons are moving around this nucleus, right, in specific orbits of fixed energy. These orbits have fixed energy, right? Suppose this is your nucleus, right, and these are your energy states, right, where electrons are moving. So these energy states, these orbits, right, have fixed energy, right? Their energy does not change. So the electron which is moving in these orbits, the energy of these electrons which are moving in these orbits is given by formula En is equals to minus RH 1 upon n square. Right? RH is your Rydberg's constant, whose value is 2.8 into 10 to the power of minus 8 joules, and n is your this orbit, which orbit it is, 1, 2, 3, whatever, right? So this is the energy of electron moving in the fixed orbit, moving in the stationary orbit, or the energy, or the orbit of fixed energy. So let's take two cases. Suppose this is an electron and it moved to a higher energy state, right, here after absorbing energy, right, or it may also move to this energy state after absorbing energy, right? So when this electron, right, will return back, because we said that when it will move after absorbing energy, it will move to a higher energy state. Now when it will move to a higher energy state, we know that higher energy state is unstable. That means electron will quickly move back to its ground state, because it will lose energy there and it will move back to its ground state. So when this electron, which is excited to this energy level or maybe to this energy level, when it will move back to its ground state, what it will do is it will emit radiations, right? It will emit radiation on moving back to ground state, or lower energy state, because this may move the electron in E3 level may move to E2, or it may move to E1. So when it will move to E3, right, when electron in E3 will move to E2, it will emit radiation of, say, this wavelength lambda 1, and when this electron in E3 will move back to E1, it will emit radiation of different wavelength. Similarly, when E2, right, will move back to E1, it will emit a different wavelength, right? So you see here, when electrons are getting transitioned between different energy levels, they are emitting radiations of different wavelengths, right? Since the radiation consists of different wavelength, and we said that every line in the spectrum corresponds to a different radiation, corresponds to a different wavelength, right? So now it's little clear how we are getting these multiple lines. We are getting these multiple lines because electrons are transitioning from different levels, right? The electronic transition is taking place between different levels. For electrons from E3 are falling back to E2, they are moving to E1 also. From E2 they are moving to E1, right? So maybe there are more higher energy states, right? So electron transition is taking place between different energy levels, and the the wavelength of light which is emitted by transition between two energy levels is different, right? We'll just see this, and using this formula we'll understand it quantitatively. Since we said that the energy of the electron is given by this formula which is moving in a specific orbit, right? Now let's take the case when an electron transition from energy level I initial to energy level F, EF. EF is F stands for final and I stands for initial. So when this, say it moves from I to F, initial state, we are taking the case of emission. So when electron will move from higher energy state to lower energy state, it will emit radiation, right? It will emit radiation. The energy of that radiation would be given by the difference in the energy of the two energy levels. Because we said that this has E2 energy, this has E1 energy. So when electron transition is taking place between E2 and E1, the energy would be EI initial minus EF. Initial is this. Initial is E2, right, which is higher. Right, this is higher in case of emission and this is lower, so delta E would be positive, right? Electronic transition is taking place from higher energy level to a lower energy level, right? So I'm sorry, it should be EF minus E1, EI, final minus initial. This is the relation that we would be using, right? So the energy gap between two orbits is given by this equation. What this equation is basically telling us, the energy gap, this is telling us energy gap between two orbits. Orbits here are this final and initial. This is the final one, and we know that in case of emission, the final is the one which is below, right, which is closer to the nucleus, and one which is closer to the nucleus has lower energy. So this final has lower energy and this initial has higher energy. So lower minus higher would be negative, right? So energy of the radiation emitted when electron moves from higher energy level to lower energy level would be negative. Similarly, when absorption occurs, when electron moves from lower energy level to higher energy level, so final is higher energy level, this would be high, this would be less, so delta E would be positive for absorption. For absorption, delta E is positive. For emission, delta E is negative, right? And this delta E shows you the energy difference between two orbits, right? And if I put this value over here, it would be minus RH upon NF square minus RH upon Ni square. This would be RH would be common, 1 upon Ni square minus 1 upon Nf square, right? So you will see that this is RH, Rydberg's constant value is this, right? This is the formula for energy between two energy states. right? Difference in energy between two energy states. Now if you want to find the wavelength, this is the energy of the emitted radiation, right? Energy of the emitted or absorbed radiation, whatever is the case. Now if we talk about the wavelength, what is the wavelength of the emitted radiation, right, when it falls from higher energy level to lower energy level, right? We can use the formula to find the frequency, as the formula is delta E is equals to h nu. Therefore nu is equals to delta E upon h, right? So we can put this value of delta E over here. Delta E is equals to h nu is equals to RH 1 upon Ni square minus 1 upon Nf square. Therefore frequency of emitted radiation, because this every line consists of wavelength or frequency of specific radiation, right? RH upon h 1 upon Ni square minus 1 upon Nf square, right? This formula gives you the frequency of emitted radiation, and this tells you the energy of emitted radiation, right? Now there's one more important thing. In case of absorption, like we have understood before, in case of absorption, Nf is greater than Ni, right? So this term would be Nf is greater than, this term would be Nf is greater, so this would be less. For absorption, this part is positive, right? This internal part is positive for absorption. Similarly for emission we have Nf is less than Ni. This portion is negative, right? So delta E is negative for emission and positive for absorption. The same thing that we have studied earlier, right? Now the other thing that is remaining here is the expression is similar to the Rydberg constant that we have derived over here, right? And we have already said that each spectral line that you see in the spectrum, it corresponds to a particular transition. Each line that you see over here corresponds to a particular transition, right, between two energy states, right? Similarly, there is a question once asked that hydrogen gas, right, consists of one electron. It consists of one electron, but the lines there, you see there are many lines in the spectrum. What is the reason? The reason is this sample of hydrogen, right, contains many hydrogen molecules, right? So when this is excited, this hydrogen gas will break into hydrogen atoms, and these hydrogen atoms will absorb energy, and due to these absorbed energy, the electrons will move to different energy levels, right? So there are many hydrogen atoms. All hydrogen atoms will absorb energy. So when they will return to their ground state from different energy levels, right, from maybe one has moved to this state, some other hydrogen atom, the electron in some other hydrogen atom has moved to this state, someone has moved to this state. So when all these excited electrons will move back to their ground state, they will emit radiations of different wavelengths based on this formula, right? Initial and final state would be different, right, for different atoms which are excited to different energy levels, right? So they will emit radiations of different wavelengths, right? So since they are emitting radiations of different wavelengths or different frequencies, you will see a line, right, for every wavelength or frequency or for every radiation, right, emitted when electrons in hydrogen atoms will return to their ground state from different excited energy levels, right? So I hope this is clear, right? We will just talk little more about this hydrogen spectrum in a different video, right? I hope this is clear. Thanks.